Welcome to class 24. This is the last class of the year, aside from the review session, review class that we'll have next Tuesday, which is a pretend Thursday. So don't try to explain it, just accept it. So we're going to talk about entropy as a rate equation. So should I go through this as writing it down, or I'll do the animations? A little easier on animations. So recall that we had this equation in 634 where we were, not only do we have the entropy that's based on this definition, which is, the changes in entropy are going to be equal to the change in heat divided by the temperature across which that heat exchange happens. We also add in this entropy generation. And so this is really associated with irreversibilities because of a process, right? This is still irreversibilities, but this is irreversibilities because of a process. And we also could turn that equation into, we could do some integrating in here, so we could have the actual change in entropy is going to be equal to the integral of, all of the heat exchanges that are happening between two states, but also with that entropy generation right there as an actual thing. And so we're always generating entropy is one of the things we learn here. Now, if we went ahead and take the derivative of the equation 636 with respect to time, we could turn that into an S dot. Or more interestingly, we could turn that into like the change of the entropy within a control mass as a rate in time. And if we go ahead and make this a steady system, right, we can set that equal to 0 and then just focus on this. So that's going to, what we're really doing is looking for the sources of irreversibilities, where irreversibilities have been generated. We have examples that follow the stuff that I've just described right here. But let's take a look at some interesting things as it's, using this rate kind of concept as an entropy rate. So let's go back to a Carnot engine, right? So this is a heat engine that we covered in chapter 5, where we have a high temperature source and a low temperature sink, and that heat from that source is put into our engine. We're able to extract work out, but we must reject some heat for this to work. And then, of course, we set ourselves with an efficiency based on this. But let's take a look at both the energy and entropy equations for this heat engine right here. So here's the conservation of energy, positive heat rate in, negative heat rate out. And then, of course, that generates work out, which is, we always use negative as so that's understood already. And this is for a system that's in steady state, so it's going to be equal to 0. And then, of course, so up above, we're going to call this the entropy equation right here, and that's equation. I guess you just take a look at equation 642 as a rate, right? So we have the summation of them, and of course the heat, the H dot, the Q H dot is coming in, so it too is positive, and the Q L dot is going out, and that's by definition negative, and we're divided by the temperatures, and now we have that S gen. So let's manipulate this equation just a little bit. Let's find what the QL is going to be. So we just solved this entropy equation for Q dot L, and now we can place that back in. So let me draw. I like to draw things. I like to draw on these things. I wish I had a stylus on here, but I'm going to use my mouse. So we're going to put this thing back into here, and this is what we get right here. So here is, well, we've rewritten this equation right up here. We've written it up here, and we now, I guess, we'll put it back into there, right there. But interestingly enough, if we take that QH out, you should recognize what we have here. That is the Carnot efficiency, right, into this Carnot second. But we also have this other stuff over here. So we can start to think of that as being, okay, so what is the work that we would get out if we had the Carnot efficiency. We would just multiply the Carnot efficiency by the heat rate in, and then noticeably we could just dub this thing right here, just call that losses. Those are now losses. We could call all this right here, this is the same thing up here as down there, right? And so what we could also say is, well, okay, well, if you take the Carnot efficiency and then you get rid of losses due to this the heat generate, the entropy generated, you would get to what the actual efficiency would be. So that's a pretty good conceptual thing to hold on to and to try to then it kind of tells us what we're really, one of our approaches to trying to improve the efficiency of a system is to minimize those losses. And then if we're going to try to minimize those losses, kind of try to see where they were generated. Where was the entropy generated? So that's what I think is the usefulness actually of this section of the book. You can also apply it to the refrigerator, the Carnot refrigerator from chapter 5, right? Now, of course, we're moving this thing around. We're putting work into the system, and we are extracting the cold temperature out, and then we're expelling it to the high, right? So this is the ice box, and this is the condenser in the back of the refrigerator, and here's the motor that's running the compressor that's making this whole thing possible. So in the same way we had before, but of course we now are going to put work power in, so that's positive. And now the cold is coming in, right? The low temperature, flow of heat, and then of course we're expelling this high. So the entropy generation equation right here is in a similar vein in terms of the signs, except for this sign right here is always positive because we're always generating entropy. So we could go ahead and solve that equation here for the QH, and then rewrite what we had up above. I guess we didn't rewrite it. We just went ahead and shoved it back in. So it gets shoved back into there, right there. And if we will recall what our coefficient of performance is going to be for a refrigerator, a Carnot refrigerator, it looks just like that. So we could say, okay, well, here's our losses, and we in the same way, if we want to improve the performance, which is the amount that we're moving, cold heat, lower heat, removing heat from an ice box or freezer or your air conditioning from your house, you want to minimize these losses and you can improve your system. So here's some of the statements that we made. We get the maximum benefit for a reversible process by having the rate of the entropy generation equal to 0. It gives the maximum amount of work for a given heat input for an engine, and for a refrigerator it gives the maximum amount of cold or low temperature heat flow for a given amount of input power. For a reversible device, and the analysis predicted in the Carnot engine efficiency, for a reversible device, the analysis, what we just did up here, right up above, that actually is sort of a quasi-derivation. We ended up with the Carnot efficiency, right? So, and we ended up with the Carnot coefficient of performance. And then for an actual device, the analysis shows that the decrease in performance, the lower output of power in a heat engine, and the lower flow of low temperature heat is directly proportional to that entropy generation. And as I mentioned, so this gives us a tool to try to identify and quantify where did the losses come from. That's based on entropy generation. So we'll do some examples in the next video.